Welcome to the TrueAllele user webinar. We're hoping to start these more frequently, and some of you will be receiving an email soon because we're also looking for volunteers. So if you have a interesting topic you would like to share in one of these webinars, feel free to contact us. Also, someone from here will be reaching out. So thanks for joining us today. Today, Dr. Mark Perlin will be presenting on um, error rates and LR distributions, how we use them, why they're helpful, the type of context they provide. So I don't have too much business to get started. I will say, however, that we do have a lot of people online today, so please stay muted. If you have a question, we're more than happy to answer them at the end. It's probably easiest to submit them to chat since we're about 40 people in here. But at the end, we'll go through and I'll chat for any questions. Other than that, I will share my screen so that you can see the presentation. Would be smart. And then I will hand it over to Mark.
Great. Thank you, Matt, and thank you, everyone, for coming today. The main questions we got when people were giving their views on what they wanted to hear about was about reporting error rates and LR distributions, something that we've been working on and writing about. And so this presentation is customized to the sorts of questions that you have been asking about. So LR distributions and error rates. Next slide, please. So I wanted to start with something familiar. In your validation studies, you see non-contributor distributions where you have what's the distribution for a laboratory of non-contributors, which gives you a sense of the specificity of your lab. This is taken from a validation study published over 10 years ago with Virginia. And this is a picture of a distribution that's a non-contributor distribution. So what are we looking at? Here is 0. Matt, I assume people can see my mouse.
Oh, probably not. Sorry. I'll have to for you.
Sorry, thank you. So here's 0 on the axis in the towards the 0, which is 0 log LR. And what we see is a mass of probability from the study of negative log LRs, exclusionary statistics. And so that's what we're looking at is a non-contributor distribution. How is it made? About 100 casework genotypes were compared with 10,000 randomly selected from each of 3 different populations profiles in order to calculate 1 million match statistics times 3 and collate them. That was a project that took people months working on that. And the way it's used is to understand the specificity of the laboratory and its genotypes. These are mainly 2 and 3 contributor mixture genotypes, as well as to calculate error rates. And so that's what this is used for. We'll come back to it, but I wanted to start with something that was reasonably familiar that you might be doing in your validation studies already before we moved on to the next set of questions. Next slide. So these are the questions that'll motivate how we're starting. So that what I just showed is for an entire laboratory on the validation with 100 genotypes. What about an individual evidence genotype? How can you use this for reporting casework? How do we construct, or how do you construct an LR distribution? How do you get error rates from an LR distribution? And how do you report it? What language do you use? So to make this concrete, let's start with a case that we worked on. Next slide. For a federal prosecutor. And this is US versus Curtis Johnson in Louisiana. In 2013, there was an armed robbery outside a bank. The truck guard was killed in a shootout. There was a bandana collected from the crime scene. There was a 70 picogram sample run by the lab that was a 3-person mixture. TrueAllele separated out the bandana genotypes, and comparing a 27% contributor with Mr. Johnson, the likelihood ratio was 200. When we got the case years later, there was a Daubert hearing about reporting low match statistics. The judge admitted the evidence. There was a trial. There was another trial a year later. Johnson was found guilty and sentenced to prison. That's the background of the case. Next slide. So what I'm not talking about today is the mathematics of how we construct LR distributions. That's been published. This was 2018. I've given many talks on this at AFS and other forums. The basic concept is using very well-established math, some of which goes back 300 years. There's a complete, fast, easy, and accurate way of constructing these LR distributions. They're essentially equivalent to comparing with all possible trillion genotypes that could possibly exist. The calculation on an evidence item takes a fraction of a second. It's easy to do because you're using software, and the resolution that we have the system set to is 1,000th of a log unit. So it's highly accurate. And with this capability of this patented technology for very rapidly constructing exact distributions that are complete across the full range of log LR values, you have a tool, the TrueAllele Viewer Distribution View, that lets you use this technology and not worry about how you might do it by hand. Okay, so Matt is going to show us the distribution view, and then we'll talk more about the case.
Okay. So, what I have here is the viewer module chooser. And so all of this happens in the report module, which I'm sure most of you are familiar with. In order to get a distribution, I'm just going to show it this first time. Literally all you need to do is just import the genotypes that you would normally as if you were just like looking at a case. So here I'm just opening up a file. I have an evidence genotype, a reference genotype, and a population. The reference isn't actually needed for this. All you need is an evidence genotype and a population. And then to calculate the distribution, and this will happen live as I'm doing it, I just go to Window Distribution. And so now we have our distribution open. The first thing that we see here is a non-contributor distribution, and then that green arrow is where the reference falls on it. And if I want to see the other half, the contributor distribution, it's just up here in the toolbar. And so that is all that's needed to calculate these distributions, and that is like a live demonstration in the sense that like that's all the more time it takes. Would you like to talk further about this, Mark?
Yes, thank you. Could you make the fonts bigger so I can see them? Thanks. Thank you. So let's just start with the contributor distribution. Turn off the left one. Thanks. And so what the contributor distribution is it's when you compute a genotype, there's a true contributor. There's a true genotype person who generated this. But given that in science we're working with probabilities, unless you have an exact single source profile that's perfect, when you make comparisons, what you're looking at is if you were to look at all possible genotypes, these are the likelihood ratios that you would get when you compare this evidence genotype with the correct person. It's a distribution. You see that it's to the right of 0. And in this case, there's a comparison that's made that's falling within this bell curve. And in the limit, these are bell curves, especially once you get up to 15 or 20 loci. And what this is telling us is that if you view log LR of 0 or an LR of 1 as a way of classifying, then a match statistic to the right, the green arrow that we're looking at that's sitting at 200, has been classified as a contributor. It's falling in the distribution of the match statistics that we expect of the true person who contributed their DNA. But the question for an error rate is, what if you misclassified? So showing, in addition to this, the non-contributor distribution, the question is, what if we have a score, this log likelihood ratio, and it actually came from the curve on the left? What's the chance that we're making a mistake? And that chance that we're making a mistake is the area under the non-contributor curve. So actually, Matt, turn off the contributor distribution. That's the non-contributor distribution. This is the equivalent of if you had compared the evidence genotype that was separated out for this contributor with all trillion possible genotypes, except that there's some math that does this for you with Bayes' theorem that's described in that Helion paper that constructs it exactly so we can work with it. You can see it, we can calculate with it, and you'll be able to report from it. And so the chance that a match statistic of 200, where the green arrow is, actually is misclassified and would belong to the non-contributor distribution is the area under the curve to the right of the green arrow, which we can highlight. You might be able to see a little of it.
I can zoom in.
Okay.
That was not the right number.
No, it's not that.
There you go.
And so that area that's not showing it from 0 to 5, that area under the curve going out to infinity, but there's not much more past 5 log units. That's the error rate. And so if you want to understand how this works, you can look at the pictures. We find just looking at the curves to be helpful. And then within this interface, we can generate information about the distribution curves as well as the error rates. Do you want to show that, Matt?
Sure. So actually, let me zoom back out so that this makes sense.
Okay.
That works. In the table menu, we have both distribution, error rate, and bidding tables. Distribution will give us information like what is the mean of these curves. So here is -5. That's about the mean of this non-contributor curve. We can do these same statistics for the contributor curve. We can also answer that question of how much area is under there in the error rate table. So right here, and I'll change this to a 1 in value. Mark, if you want to talk about the 1 in value, I don't know if you wanted to get there yet.
It's
Okay.
fine. You can show it both ways. So you can see it as a fraction, but most people, including juries and lawyers, would understand a number like 1 in 4,000 more readily than a fraction. And so we usually report it that way. People who study communicating statistics to non-mathematicians recommend using whole numbers and not using numbers like. So you can do it either way, Matt. You can click on a button and be obscure if you'd like, but most juries or judges wouldn't know what you meant by 2.49 to the times 10 to the -4th. So, okay. So this is the ability to report error rates. And now that's probably enough on this. Do you want to show the next slide?
1 second.
So what we're going to show now is the basic language when you start reporting error rates, we have detailed protocols. Obviously, will help you get started with this. And we have language that we've used in our reports, hundreds of times in report. To summarize the likelihood ratio shown in blue, we'd say a match between the Bandana and Johnson is 200 times more probable than coincidence. That's with the most conservative ethnic group. Now, how do we report the error rate? How do you describe? You're not going to start talking about calculus or areas under curves or statistics. But this is accurate language, and you can say that for a match strength of 200, which is the likelihood ratio, only 1 in 4,000 people would match as strongly. And that's language that we find that the lawyers, judges, and juries get. It's English. And then we might give examples of what do we mean by 1 in 4,000, how many people would that be, however you'd like to describe numbers that you're comfortable with talking about numbers the way you might with RMP. I want to point out that when we're talking about error rates, there's a fundamental theorem that has been observed by many people, not in forensics, in many fields of information theory, statistics, Bayesian analysis for almost 100 years, ever since Markov's theorem. Markov reproduced Chebyshev's theorem under his own name. Chebyshev was his teacher. And that's the key to this proof. I'm not going into it, but there's a concept that whatever the likelihood ratio is, the error rate is bounded by 1 over that number. If the likelihood ratio is 1,000,000, the error rate can't be more from a Bayesian system with probability. It can't be more than 1 in 1,000,000. It could be 1 in 1,000,000,000,000. It could be 1 in 1,000,000,000, but it's not going to be 1 in 100. And in this case, we see that the likelihood ratio is a bound of 1 in 200, and the error rate of 1 in 4,100 is less than. This is useful in court if you have a large match statistic or any match statistic, and somebody asks about error rates, you can always say that an upper bound on the error rate is 1 over whatever your match statistic was, and that's always true. Continue. So the next question is, what about exclusionary error rates? And let's go through this, and you'll see something interesting. I don't know how many labs are reporting exclusionary rates. We do a lot of this for anybody who needs it, innocence group or defense group, or even prosecutors who want to show that somebody's not there. Next. So here's the case. It was an innocence case in Georgia. 17-year-old Kerry Robinson was wrongfully convicted of rape in 2002, sentenced to prison for 20 years. The Georgia Bureau of Investigation analyzed the vaginal swabs. They developed STR data from the 3-person mixture. TrueAllele found an exclusionary likelihood ratio of 1, roughly 1 in 100, 1 over 1 over 3. And based on this, what Cybergenetics reported, this new exculpatory DNA evidence, and his conviction was vacated. He was released. Next. Do we, I think,
Yep.
back up?
Yeah.
Back up.
Sorry.
And let's take a look at what TrueAllele is showing us.
Okay. Get rid of that one.
Okay.
Bring this one in. Oop. Okay, so what we have here is the evidence from there compared to Kerry Robinson. And so let me just open distribution here. And so you can see that he is in the non-contributor curve. And if I turn on the contributor curve, you can see that almost as an inverse of what we saw previously, now he's in the tail of that contributor curve.
Right. So the whole point of this is that it's symmetric. There's a dual relationship between these non-contributor and contributor distributions. As far as the math is concerned, your hypothesis is just the flip of what you had before. and you're just looking from left to right instead of right to left. The Bayesian math doesn't care. So if you just keep the non-contributor distribution on, as Matt said, this is the distribution of people who didn't contribute their DNA, and the match statistic is being, if you had a threshold, which is standard in forensics of 0 log LR, is that he's being classified as not being a contributor because he's falling to the left of 0. The distribution of non-contributors is showing where he's falling in that. And then the question is, what if he actually was a contributor, but this evidence is misleading? And so turning on the contributor curve, you can leave the other one on that. Turning on the contributor curve, you see the two of them together. And there's enough resolution here that we're seeing that Robinson's match statistic, the green arrow, is separated from the curve on the right, the contributor distribution. He doesn't look like he's a contributor. Now turn off the non-contributor. And the question is, by how much? Can we quantify this? It's one thing to tell the court, well, the green arrow is to the left of the bell curve, doesn't look like he's there. And maybe that's fine for some juries. We don't do that. We put a number to it, an error rate. And the error rate here, the way you quantify in statistics, it's called probability of misleading evidence, which actually works just like RMP as an error rate, but for mixtures and less certain evidence, is what is the area to the left of the arrow, the contributor curve? How far away is that? And if Matt turns that on, we can see the area, and Matt will probably zoom in again, get a closer look, because with a match statistic of 1 in 100, you can see it. Once you start getting into match statistics of 1 in 10,000 or a million, you may not see it. But here you can see that error rate. It's measuring how far away would somebody be who's actually a contributor. What's the chance of an adventitious exclusion? All right, so we can put words to that by going to the next slide. And now we report an exclusionary statistic like this. A match between vaginal swabs and Robinson is 103 times less probable than coincidence, still using a number like 100 instead of 1 over 100. And in red, this is our exclusionary language. For an exclusionary statistic of 1 over 103, the likelihood ratio, only 1 in 3,730 people would be excluded as strongly. This is where we're using that 1 in feature in the distribution window. Because the likelihood ratio is flipped to the other side with the hypothesis for exclusionary results, the law is the error rate is less than or equal to the likelihood ratio because we flip the hypothesis. And as you see, 1 over the LR would be an upper bound on the error rate, 1 over 103. And here it's about 30 times less, 1 over 3,700. That's how we report this. All right. So that's the beginning of showing this duality between, in any Bayesian system of which TrueAllele is one. It makes no difference if you're looking at inclusions or exclusions for error rates, likelihood ratios. The math is the same, the pictures are the same, and the computer's the same. Next. So that was looking at one evidence genotype. What about validation studies? And the validation study for your software, you're looking at sets of genotypes, maybe of similar characteristics, numbers of contributors, match statistics, mixture weights from a laboratory. And your question isn't about the evidence, it's about the laboratory process. So continuing, This is the same non-contributor distribution we saw in this paper that's on our website and free online to take a look at. It's very nice paper. Susan Greenspoon and Lisa Schimmer Wood were great to work with on this. We kept putting more in until everybody was happy with it. The first question is, what does this tell you about error rates? And I'll show you that right now. There's also a question about speed. If you collect 1 million comparisons, that might take a lot of human time and maybe computer time. And also, these methods of comparing with random genotypes population, they're great for inclusionary error rates, but what do you do for exclusion? How do you get those? So let's first take a look at this error rate question. And the next slide shows a picture that's in the paper. Here, in over 1 million comparisons per ethnic group, we could look at the tail distribution. And so these are the log units 0, 1, 2, 3. If you back up, Matt, we can look at that right tail. And there at the bottom, right of the curve, you see there at the 0, 1, 2, keep moving to the right, Matt, to the right. 0, 1, 2, 3. You see almost nothing there. That's the area under the curve that's related to the probability. But what's in that bin and further to the right as well will give you the error rate. Next slide. And so here we see that for match statistics in bin 0, those are numbers like between 1 and 10. There were a few numbers that were greater than log LR 0. Oh, that should be log LR equals 1, greater than 1. That's okay. We'll keep going. We updated these slides to put a lot in today, so we'll fix them up when we post them. And then for bin 1 is numbers between 10 and 100, and we see how out of these million comparisons, the number of people, the different ethnic groups. And two, by the time we're up to more than 1,000, we're seeing virtually no error. And this is what we reported, we've testified on. What's the false positive rate? For likelihood ratio greater than 1, the false positive rate is less than 1 in 20,000. Once you get up to over 100, it's less than 1 in a million. And in fact, for any reported log LR value, you can look up the false positive error rate going back to the curve as we just discussed by getting the area that's under the curve. Okay, so Matt, I think you'll be showing. So what is the point of what, no, onto the demo.
Yeah,
So
sorry.
what we're showing is that instead of taking months, I asked Matt to generate this while I was talking and tell us how many seconds it took, or minutes, I don't know. Did you time it?
Yes. So what I did to generate this is these are all the genotypes from the Virginia validation. Loading all that in and then doing the likelihood ratio calculations took about 22, 23 seconds. And then to generate the distributions for every single one of those took about another 15 seconds. And then, so what this is this is the distribution of every single one of those genotypes. Obviously, that is a lot of information, but we can see a composite of all that. So
Let me
there's
explain what a composite is. Mathematically, for what you're doing in the validation study, is you're averaging the probability distributions, and that when Matt hit the composite button, that's what it did. It took the average of all of them. Now he's going to show you something else.
the contributor side of that.
No.
Oh.
Turn that off. So show the left, just the left. And now we're going to show you the one band binning. This is showing it to you at a milliband. resolution, 1,000 points
Ah,
per band. But what we saw in the validation paper was binned by powers of 10. Okay. And if you just change, if you get rid of that last one on the end by making the region like -29 or something, and you can get rid of the curve as well by clicking a button.
um,
Okay.
I, I, there it is. Sorry.
What you'll see is that that curve that Matt is showing you is identical to what we published 10 years ago, except instead of taking 3 million comparisons, yeah, okay. Instead of taking 3 million comparisons, one for a million per ethnic group, and then collating all of this stuff, it's instantaneous. As Matt said, he loaded it in, computer calculated, the whole thing took about a minute. And it's much more accurate. I mean, this is fine at one band resolution, but if you look at the curve, it's exact. But what's also interesting is once you have that, what we couldn't do, we could look at the 100 comparisons that we had and talk about something about sensitivity, the right side. But what we couldn't do with the technology back then was to do the equivalent of sampling for all trillion possible genotypes of everything that represents the true contributor distribution. But at a click of a button, that is the contributor distribution. That's what it is. And it's built in. And the reason you want the contributor distribution, you can turn off the left one, is because now you can do exactly the same world for not just understanding the sensitivity, but for calculating specificity for exclusions. This is the left edge of this curve, down to the left of 0 and moving leftward, is what's giving you error rates, if you want to know them, about the lab in a validation study. And so we see this duality where anything you can do for inclusionary results, turn on the left curve, you can also do exclusionary results by using contributor distribution on the right. And we use this all the time. We don't know where the cases are coming from or what the questions are going to be. And we want to be able to report match statistics and error rates, basically everything. All right. So let's move on. The talk. Let's look at questions. Okay. So we're talking about validation, and people have made interesting comments about validating with casework data. But we published with Virginia DFS on this in +1 over 10 years ago, and it's simply not an issue. Um, and it was described in the paper and written up, and the reviewers were fine with it because it's science. It's not a policy. It's just how the world works with information. So why can we reliably validate using casework data, and this notion of ground truth, whatever that means, isn't needed in order to do a validation? Well, let's see how this works. Next slide. So let me explain how we answered some of the reviewers' questions about, again, arose over 10 years ago. How can we talk about knowing that the contributor distribution is correct And this was by making comparisons, by the way, not with these math methods that we hadn't invented yet. How do we know that the contributor distribution of these match statistics that were reported on, of 100, basically from 100 to about a trillion in this study, why can we rely on them? And the answer is, we know statistically that they're classified as contributors because we look at the non-contributor distribution and look at the right tail around zero, point to that map, and because the error rate is so low from the non-contributors, we have very high statistical confidence that we're not falsely reporting contributors. And so whatever statements we made about 100 match statistics, I mean, here we're looking at a trillion match statistics, essentially, but in the paper talking about 100 match statistics, because the non-contributor distribution basically goes to zero vertically as you hit zero log LR horizontally, the error rate's so low that you can believe the contributor results. You don't need to know that there actually was a hit. You just need to know that the error rate from the non-contributor distribution is low. You're not misclassifying it. And symmetrically, it works in the dual way. How do we know that we can rely on the non-contributor distribution? It's because the contributor distribution has a very low error rate. So these two distributions support themselves, and an empirical study with 1 million comparisons produced the identical distribution with the non-contributors, but a much lower resolution. So basically, by understanding these distributions and error rates, and when they're low, that's what makes results more reliable. You can validate from any genotype. You don't need anything special. And many of the labs have validated from casework. It's not clear that everybody understands this yet, but you do. Or if you don't, you'll have questions that we'll answer. Okay, next. This is a preparatory question for what you're about to see next. Why doesn't TrueAllele need or use analytical thresholds, AT? This is a question we get asked all the time, and let's answer it. Next. The answer is, basically TrueAllele's Bayesian modeling has modeled baseline and background noise for 25 years. It was built to model this. There are variables that model what the baseline is and figure it out from the data for every locus at every experiment. And that's just part of TrueAllele. I mean, obviously TrueAllele's modeling a lot of other things, stutter, relative amplification, the variance parameters on everything it can see, the PCR variation. But in particular, it's modeling baseline and is distinguishing between what is background noise versus actual allele signal. Other parts of the system, for example, with stutter modeling, account for other artifacts that aren't noise and they aren't signal, but they're artifacts. Also, the Bayesian computing uses all the data because you can't model the baseline and reliably model all these other low-level artifacts if you're not using all the data. For example, if you're looking at a 2-person or a 3-person mixture, and you only are looking at 1 or 2 peaks per locus, you're not going to be getting much information about that sample because you don't have enough data. There's another reason that is also part of the Bayesian framework. TrueAllele explains the data. It doesn't try to classify the peaks. In science, nobody's trying to classify anything. The AI programs, statistical linear regression, there's no classification. You explain the data, and better explanations will have higher likelihood and ultimately higher probability. And so it's not a matter of how do you know that this is a stutter peak? How do you know this is background? Nobody knows. It's just data. But if TrueAllele's trying out 100,000 different explanations at every locus, those explanations include to what extent the system is saying, well, this pattern that it's trying out against the data as a model, well, maybe that is in the allelic pattern, maybe that isn't, maybe. So it's explaining the data without changing it, which is what any Bayesian program does. And I don't know, there's like hundreds of thousands of them. And the concept is to use computers to explain in every possible way instead of trying to do something impossible, like say, I know that this is a stutter peak or background noise. How would you know if you're looking at a 2% mixture component? I really don't know. Next. Okay. So this is interesting. Other software that's not TrueAllele does use analytical data thresholds. I don't know, PopStats, LRMix, all kinds of software. How does that affect LR information? And here again, the LR distributions help us in understanding what it is that we're seeing in terms of the information properties. And that's what I'm going to show you next. Okay, so California versus Alejandro Sandoval. The police collected a baggie that contained methamphetamine. The defense had the baggie tested. They sent it at a private laboratory. They found a DNA mixture. They first ran it through StarMix at 40 RFU, which saw 24 peaks. I'm not sure of that number, but Matt is because he put it in. So it's fine. So it saw 24 peaks and gave a log LR of negative 1.38 band, which is around 125, so 140, whatever it was. That's what they were. There were two baggies. And so that's what the lab reported. Other runs on this data, if you give it a lot less data and you run it 90 RFU in StarMix, you only get 11 peaks across these 21 loci. And you're getting to negative half a band, which is like a third, something very small number. If you give it more data at 20 RFU by letting more peaks in at 38 peaks, StarMix would find negative 7.5 band, which is something in the tens of millions. We are asked by the lab to run TrueAllele through this. We don't have an analytical threshold. We looked at all 210 peaks. The log LR was a little under negative 6 band, which is 1 in a million. Okay, there was an unsuccessful Dauber challenge with StarMix. The federal prosecutor dropped his challenge and they agreed to drop the more serious charge against the defendant. And this is a notable case because Journal of Forensic Sciences published some case report that was filled with many speculations about TrueAllele and StarMix that didn't seem to account for this data difference. But the question is, can LR distributions explain what happened? Because that's what we're talking about today. And I think this is the clearest explanation of the information properties. So Matt, maybe we can move on to that and see what TrueAllele did.
Yes. Okay, let me just grab the right window here. And so what we are seeing here is the distribution, non-contributor and contributor from TrueAllele. So this is the TrueAllele inferred evidence genotype and what that looks like.
Okay, can I talk about that for a second?
Please do.
Okay, so what's really nice is that when you're looking at both the non-contributor on the left, that bell curve, and the contributor on the right, and that bell curve, and they're both bell curves, is what is the overlap of misclassification? So take a look at 0 and ask yourself, to what extent is there any confusion? And on this case, it was clear enough to TrueAllele that a positive match statistic greater than log L or 0 would classify this uh, as a contributor as a contributor. And the green arrow that we see here at around -6 is being classified as a non-contributor. And because the tails are so close to 0 in the center, there's essentially virtually no classification error. So that's something to keep in mind. And now the question is, when you look at 10% of the data, what happens to these distributions? Here we have widely separated distributions. They're pretty much fully informative. If the arrow falls on the right, this confidence, it's a strong confidence, it's a contributor. The arrow falls on the left, this strong confidence is a non-contributor, it's more exclusionary. What happened when some program was starved of data? Well, let's see. And where did that match statistic fall, Matt?
Right there.
Right there. Okay, so what you see is the right distribution in that light green blue color has moved from the blue curve that's centered at around 12, which is the KL statistic, that's the average of the curve, 10 to the 12. And it's moved into the left to somewhere, if you look at the peak, that's less than 1. So it's by not having data, the contributor distribution has very little information. And from the left side, we see that the opposite KL, the negative KL, which was around, again, maybe -12, very informative, has moved in to the right towards 0. Maybe that's at around -2. Or actually, because it goes up and down, it's more like -1. So maybe we can zoom in on the lighter curve and get a closer look. So this is a star mix result. Now we've zoomed in from -6 to +4. And just look at the non-contributor distribution. So there's the non-contributor distribution, and you see that that max statistic looks like in this around, -1 in TrueAllele. We brought it into TrueAllele for this analysis. Oh no, sorry, -0.5. The scale changed. So it's 0, -1, -2. So the match statistic is around -0.5. And so that looks like it's okay. That looks like it's in the non-contributor distribution. Could you turn off that distribution and turn on the contributor distribution? Well, that match statistic of -0.5 also looks like it's in the contributor distribution. And if you turn both on, you see that there's the interval of overlap between these two distributions that goes from around -1.5 out to maybe +1.5. It can't distinguish between the two. So when you don't give the system enough data, and 24 peaks over 21 loci is not much data for a mixture. You'd ideally like to have 3 to 4 allelic peaks plus stutter. The result is the system really isn't able to distinguish between contributor and non-contributor. The distributions give what I think is the clearest answer to what's going on when you don't give a Bayesian system enough data. Okay, so let's quickly do 2 things and then wrap up. We have the next question is, why don't you need LR reporting thresholds, these RTs? Why don't you need them? And let's take a look on the next slide We took this data from a paper with Kern County, Garrett Sugimoto, and Kevin Miller, Jennifer Horniak was involved, published 10 years ago, 2015, looking at up to 5 unknown contributors. So here, for evidence, we just took the 10 5-person contributors, which gave us 50 genotypes with a wide range of match statistics. And then, well, let's call capital R the number of references, 10, 100, 1,000, all the way up to 100,000. And you know, Matt, we can skip the demo thing here. You're just going to show a composite curve. It's fine.
Okay.
In the interest of time, let's just move on. And this is what we calculated. See, what is the whole purpose of a reporting threshold? As has been explained to me by about 6 different DNA tech leads. The point of it is that if in your validation you don't see any adventitious hits, then you have confidence that when you set your reporting threshold over the level where you might have seen adventitious hits, that you're not going to see any, and your error rate from your validation adventitious hits is 0. It's really a sampling issue because that 0 error is unattainable. The first column is showing R, the number of references, as it goes from 10 to 100,000. The next column in blue, N, is 50 times that because we have 50 evidence genotypes. We have 10 samples and 5 extracted genotype, inferred genotypes. So N goes from 500 to 5 million of the number of comparisons. And then purple shows how many were positive. If you look at the text underneath, if you have greater sampling with more comparisons, and this was done the old way, with actually making these comparisons, N keeps increasing. And as N increases, in purple, you see the number of positives increase. You're going to get more outliers, more higher match statistics as you get more positives. And if you look at the red column in the table, we start off with what is the largest match statistic we saw with N equal to 500? Well, that was a log LR of 2.5. So you set reporting threshold to a log of 3, which is 1,000, and life is good. But if you were to go up to 50,000 comparisons in the third row, where N is 50,000 in blue, now the maximum statistic is over 3 log units. So now you have to go up to 4 log units. You might set your reporting threshold up to 10,000. But if you keep going, and in blue in the table, we see N going up to 500,000, 500,000. Now there's almost 3,000 positives in purple, and the largest one is 4.5 log units. So now you're going up to 4.5, and now maybe you'll start setting your reporting threshold to 5. If you keep sampling based on these distributions, it's only a matter of time before you cross any fixed reporting threshold level, because it doesn't go to 0. The more you sample, the more chance you're going to get to have some maximum outlier that will traverse and go beyond whatever you set it. And so in red, in the text on the bottom, a larger maximum LR is going to give you a larger maximum value. It's going to keep forcing higher and higher reporting thresholds. It's just because you didn't see it when N was smaller, like 500 or 5,000 or even 50,000 in a validation study, doesn't mean that it isn't there. It just means that was how much you sampled. And so the easier solution is to recognize you will always have outliers. What's the frequency of them? And that's what error rate does. So this lets you report all the LRs and provide an error rate context. Next. And this is fun. this came, how do you rebut fake science attacks? We see a lot of this. TrueAllele's had over 40 admissibility hearings at this point, Dahlbergs and Fry's and Spencer's and Harper's and whatever. Next slide. So this is US versus Ravel Mills. It's a case that we got involved in about 2 years ago. It was a shooting-related homicide in Washington, D.C. The federal defenders engaged us. We looked at a gun in a magazine that we recovered. The gun had a 6% component of a 3-person mixture with a log LR of negative 7.8, that is less than 1 in 10 million. And using logs for the error rates because they're so small, negative 11 is down to almost 1 in a trillion. There's also a magazine, which was a 2% component, 4-person mixture. The log LR was negative 11, which is a little bit greater than 1 in a trillion. And its error rate, the log LR, see, is about 1 in quadrillion. The federal prosecutor requested a Daubert hearing. He retained an expert. And the expert concocted an amazingly interesting argument. And in some sense, it was new, but in some sense, it was old. They turned quantitation that we're used to in TrueAllele and the error rates that we're talking about into old style binary logic from 20 years ago, wrote something that looked really nice, referred to our validation papers, and then not only said, is this all wrong, but boy, we're just such dishonest people, which was not nice, but lawyers will do anything, I guess, sometimes. There was a Daubert preparation. Documents were filed. The motion that I wrote for the defense is posted on our website under admissibility. And to say that the judge was happy with it, I didn't bother with a Daubert hearing. It was really clear that this attack was baseless. It's been reprised, by the way, last year in a letter in JFS that's referring to this exact argument, same argument that somebody else gave in this case. Let's see what it's all about and how it's resolved. Next slide. So, taking the JFS study out of context from 2015, the one we just saw, and saying, let's have a binary error rate. Oh, that's a problem. It's saying we're not looking at the values of the likelihood ratios, even though scientists know that the stronger the likelihood ratio, the smaller the error rate. So that's ignored. Let's do it in the actual software version of the case, not what was done in the study. We see that the argument they're trying to make is that in a mixture range of 1 to 5%, there were 7 counts for a likelihood ratio of less than 1, that was 35%. And for another 9 comparisons in the mixture range of 5 to 10%, well, in this case, there were none when you recalculated. So looking at match statistics under 5%, TrueAllele has a 35% error rate. What are we doing? Well, the simple answer is that binary error rates are simplistic and irrelevant. Why? The likelihood ratio is quantitative. It's not saying that a likelihood ratio of a tenth is the same as a likelihood ratio of 10 trillion. That's just stupid. But that was the argument. And the point is the likelihood ratio is quantitative and the error rate depends on the LR magnitude, as I showed you before. Next slide. And here are the actual numbers. The case has begun in the magazine. The mixture weights are 5 and 2.5%. The log LRs are -7, -11, with very solid error rates. And from this validation study, we see very much smaller LRs. Some of them are -0.5, the bottom one's -0.15. So these are very small log LRs. What do they have to do with the LRs in the case? Here's where the distribution helps. Next slide. So there's the non-contributor distribution for the gun on the left. There's the contributor distribution for the gun on the right. Green is showing this match statistic of around log LR -7.5, -8. And what you're seeing in red is that those are error rates from a different study. It's not this case. It's completely different. We'd even have a different distribution. And they're not even close. You're talking about something else. You're talking about the type of low contributors on maybe like a 1%. You're just seeing low match statistics that have higher error rates that are known to be higher, that are hanging around zero and have nothing to do with this case. They're just not relevant to this case because a log LR of -0.5 is not the same as a log LR of -7.5. And the distributions are showing you where you are along these curves. Next slide. For the magazine distributions, you have something similar. On the left is the non-contributor distribution, on the right is the contributor. And the green arrow is the match statistic to the defendant. It's -12, 1 in a trillion. And what is being purported as having the same stature is, again, around zero from a different, something else. And it's just not relevant. And the judge saw that. And TrueAllele was found to be reliable because equating very small LRs with very large LRs and ignoring these distributions and error rates is not modern science. Next. So, to wrap up, how do you always report the true information from your DNA evidence? And I'm hoping after today that some of you will be contacting us about how we can help you do this, show you how to use the software, whatever it is you might want to validate, how you report it, how you testify about it, and how you can comfortably deliver all the information from what is coming into your laboratory. First, use a fully Bayesian model on all your STR data with no thresholds. You're doing that already, no analytic thresholds. Have TrueAllele separate your mixtures into contributor genotypes. You're doing that already. Thirdly, this is the new part, report all likelihood ratios, both inclusionary and exclusionary, without a reporting threshold. That's the part many of you are not there yet. Why can you do it with confidence? Because of step 4. You can use the distribution function that you have to report error rates, giving a frequency context for every likelihood ratio that is making it from the software into your report and into your testimony, explaining that low match statistics have a higher error rate, putting a number to it, and higher match statistics have a lower error rate. And you're not overstating anything. If you want to report a very low match statistic, give an error rate. And the courts are fine with that. The juries are fine with that. So I think I'll stop there. We've covered a lot. We'll post this so you can look at it again. If you have questions now, I'm happy to take them. If you have questions later, we're happy to take those as well. So Matt, give the floor back to you.